Hey everyone, today I'm showing you a new quick release ground control point base plate that I reverse engineered from 3D scan data. In this video, I walk you through my reverse engineering process using BricsCAD, a budget-friendly CAD tool. This new base plate works with the Falcon F38 quick release system, so you can swap it out fast and mount it onto a monopod. That way, you get extra height during your LiDAR scanning sessions. In the US, BricsCAD runs about $1,752 for a lifetime license, but in Thailand it's much more affordable at around $1,056. So basically the price is localized. It changes depending on where you live. Many of you have been looking for a cheaper CAD option since Autodesk's Inventor package, including the recap, runs a hefty $3,500 per year. Fusion is cheaper, but it doesn't support point clouds, and FreeCAD still isn't fully mature yet. So right now, BricsCAD really fits the bill. With the Pro version, you can model complex shapes with ease. For example, here's a car fender flare sent in by a viewer. Since BricsCAD supports lofting with curved 3D rails, parts like this can be modeled directly, something FreeCAD can't handle yet. And if you have got a LiDAR scanner, you will really appreciate this. With the Pro version, BricsCAD lets you convert point cloud terrain scans into thin surfaces and then generate contour lines from them. And normally, features like this are only found in higher price CAD package such as Autodesk Civil 3D. Before we get started, I need to do an additional 3D scan of the Falcon F38 bracket. This time, I'll be using the Creality Sermoon P1, an all-in-one 3D scanner to make the scan. I will connect it to the PC in wireless mode to speed up the scanning process. In wireless mode, you don't have to deal with bulky cables or an AC adapter while scanning. Since the object has a black powder-coated finish with some surface roughness, it's difficult for the scanner to pick up. To solve that, I apply a spray which helps capture the scan faster and also improve precision. Since the part is very small, I set the resolution to 0.1 mm and start scanning with the 7-line laser mode. I will scan just the front and back sides and then align them together. It's important to capture as much of the sidewalls as possible since they will be used for overlapping when aligning the two scans. In this case, I need to switch to single line mode to capture the side, since the 7-line mode just can't get the sides. The front side is easier to scan because the sidewall is more exposed. When making a 3D scan, it's important to set the resolution properly. From this scan, I expect about 400 to 500,000 points in the cloud. If I lowered the resolution to 0.15 or 0.2 mm, there wouldn't be enough detail to trace the lines accurately when reverse engineering in CAD. The more scans you do, the better you will understand which resolution settings you need. After completing both scans, I fused point clouds using a 0.1 mm resolution. Then I trim out the unnecessary parts. Don't trim too much though, since you need the sidewalls for overlapping during alignment. Next, I opened the alignment menu and oriented both scans into the same position. I use the threaded slotted holes as a reference since only one side of the hole has threading. Then I selected 3 pairs of reference points to perform the alignment. And here we go. The 2 scans are now successfully aligned. Because the sidewall from the first scan is deep inside, its quality is poor. After finishing the alignment, I trim it out so the cleaner sidewall from the second scan dominates the result. I turn off the Penetrate selection tool so I could carefully select only the outer sidewall and delete it. When I turn the second scan's visibility back on, I will have a clean scan ready for meshing. I set the number of triangles to 1 million, which matches the current face count. And here we have it, a nice clean scan from the Sermoon P1. You will get similar results with the Sermoon S1 and the Raptor scanner. Next, I will export the file in ASC point cloud format. Then I imported the point cloud into CloudCompare and adjust it to the brighter color since this option isn't available in BricsCAD. I use 3-point alignment to position the bracket's bottom face onto the XY plane. Now the bottom face is flat and aligned with the XY plane. Then I rotated the model along the Z-axis to align one side with the Y-axis. The scan result from the Creality Scanner's 7-line laser mode consistently produces thin wall and clean data for reverse engineering. Among the group, the X1 delivers a superior performance with a higher precision. Because BricsCAD can import point clouds directly, I will save the file in LAS format. Here's in BricsCAD, and this is also my first time using the software for reverse engineering. I activated the modeling toolbar. Click on the point cloud and choose Import Attach. The import process is quite straightforward. In the Render Settings tab, you can adjust the point cloud size. I have set it to 1. The point cloud is stored in the point cloud layer, and I will create 2 additional layers, one for sketches and one for solid. For this demonstration, I will enable Lightweight to improve visibility. BricsCAD uses an AutoCAD style modeling workflow. The 2D sketch will be created on the XY plane, which is the default World User Coordinate System or UCS. Now I'm creating a mirror line at the center of this horizontal line on the default UCS, also known as the World UCS. Now I'm drawing a line from the center of this circle, matching the hole and extending it down to the bottom face of the base plate. Next, I move the UCS by snapping it to the tip of this line, and any sketch I draw will be created on this new UCS. Just like another CAD tools, I trace the line along the base plate profiles, then use a 3-point arc for the round corners, and finally trim away the extending lines. Next, I select the lines on the right side and mirror them to the opposite side using the vertical line I drew as the mirror plane. I select all the lines and use the join command. Now I have a closed loop. In the modeling tab, I click extrude and set the height to 8.1 mm. I then switch the view to X-ray mode so I can see the point cloud. Next, I'm going to project this circular hole onto the top face of the solid. I also project the mirror line onto the solid. Next, I will select the entire point cloud along with the sketch, then move the whole center to the origin. Now I have a solid with faces, so I can draw the sketch directly onto the surface without moving the UCS. The software detects the pointer location and automatically snaps the sketch onto that surface. Sometimes this causes the sketch to lag while drawing, so I prefer turning off the solid layer for faster sketching and better visibility. After finishing the tracing, I joined all the lines and offset them by 2.6 mm to define the wall thickness. After mirroring the lines, I joined them to form a closed loop. Now I can use the push-pull command. The software automatically detects the loop, and all I need to do is define the height. I select all the entities and hide them. Next, I will import the FileCam F38 bracket scan into the drawing. Next, I create line and circle to define the center of the point cloud. Because AutoCAD style CAD tools are very flexible, they let you create 3D lines quickly. You don't need a plane or to create a new sketch. You can simply move the entire point cloud by snapping it to the reference sketch. Now the F38 bracket is precisely aligned with the base plate. Here I need to increase the thickness of the base plate because the fit is too tight. I move the F38 point cloud into a separate layer so I can turn it off when needed. I use the push-pull command to increase the bottom thickness by 2 mm without creating a new sketch. Now I have enough space, but the LiDAR scanner's work point will be 2 mm higher. Unfortunately, the F38 is already the thinnest quick release plate available. Next, I will extract the boundary from this face into a sketch and move the UCS here. Then I will turn off the solid layer for clear visibility so I can freely trace the F38 profiles. Yes, I can draw a sketch directly onto this face, but pointer detection makes it lag and feel annoying. It might be fine for a rough sketch, but not for precision tracing. I offset the line by just 0.1 mm to provide clearance. This ensures a proper resistance when sliding into the bracket. Achieving this in a single pass requires a high precision 3D scanner. Next, I will use the push-pull command to extrude cut the F38 profile into the base plate. Next, I will use the extrude command to extend the same sketch and fill the cut profile up to this point. Because I use the extrude command, I now have two solid bodies. I will weld them together using the union command. Next, I will project this bottom edge onto the top face, offset it by 1 mm, and create a boundary sketch for cutting. This time I'm using the direct modeling feature. It's faster when I'm not tracing the point cloud. I use the push-pull command to extrude cut with auto-detected boundaries, snapping it to the bottom of the profiles. Next, I will extract the boundary sketch from this face and move the UCS to this location. Next, I will trace the sketch on this corner to pull up the solid. Since BricsCAD doesn't allow mirroring the features, I will mirror the sketch instead. I simply pull the profile upward and snap it onto the top face. Next, I will extract the sketch from this edge and move the UCS to the midpoint of this line, then rotate the X or Y axis 90 degrees until the UCS is oriented in this position. Next, I will trace the F38 profiles as shown, offset it by 0.1 mm for clearance, and join the lines to close the loop. Next, I will extrude the profile in both directions and weld the two solid bodies together using the union command. Next, I will create two 3D lines on this corner, then use 3 points from the sketch to align the UCS. The modeling process is flexible. You can't simply create 3D lines anywhere. Then I trace a similar profile, offset it by 0.1 mm, and close the sketch loop using the join command. I mirror the sketch to the opposite side using the mirror line I created at the beginning of the tutorial. Then I extrude the corner profiles one by one and weld the solid bodies together using the union command. Now the F38 bracket is locked on 3 sides, which is more secure than locking with just 2. I use the direct modeling tool to create this boundary and pull it down, reducing the base plate thickness to 4 mm. This makes the model look less bulky. Next, I turn on the base plate point cloud, draw a center line, position the circle, and use the extrude command to cut it down with 30 degrees taper angle. Next, I create a direct sketch on the bottom face, offset the line to leave a 1 mm gap, and use the array command to replicate the 4 slots. Then I create a 5 mm circle and trim on the inner lines, join the lines together. Then I pull it down to cut with this profile. Next, I apply cosmetic chamfers and fillets in a mechanical design practice. This is typically the final step a designer performs. At this stage, BricsCAD performs well without any errors. I'm able to fillet and chamfer all the corners. This software is geared more toward reliability than a fancy user interface. So now the modeling is finished. Here are my thoughts on BricsCAD for reverse engineering. With its AutoCAD style workflow, BricsCAD makes creating 3D sketches and lines fast without requiring planes. The closing loop is straightforward and hassle-free. The snapping tool is on par with other professional CAD software, and moving or aligning point clouds is both easy and accurate. For solid modeling, performance is comparable to Autodesk Inventor. The drawback is that execution commands aren't retained, so making design changes later is difficult. For reverse engineering, this usually isn't an issue, but if you are designing around scan data, re-editing the model becomes challenging. For exporting the file in STL, you can set the output mesh resolution. For comparison, I will also export the file in step. Exporting in step format results in approximately 25,000 faces, but this can be adjusted in the slicer. And for the STL export with high settings, I only get about 7,000 faces. This results in a polygonal appearance in the STL file. It may be acceptable for FDM printing, but with resin printing, the facing will definitely be visible. But the step file looks super smooth with its 25,000 faces. When importing the step file into FreeCAD, you can see it's a pure CAD file with infinite resolution, which allows you to continue modeling seamlessly in FreeCAD. When I open the DWG file saved from BricsCAD in AutoCAD, it behaves just like a natively created AutoCAD file with all layers and settings preserved. I will include download links for the point cloud and step file in the description. BricsCAD offers a 30-day trial, so you can follow along with the tutorial. To install it, loosely attach the F38 bracket and ensure the slotted holes align as shown. Next, slide the battery grip into the base plate. You may need to twist it slightly to match the curved profile, then tighten the screw at the bottom. So now you have a ground control point base plate that can be used with a monopod. For the S20, I printed in gray to achieve better color matching. If you are using the original S20 hard case, the battery with the F38 may feel slightly tight, but it does fit. Okay, thanks you guys for watching. I'll see you in the next video.